Hey there, fellow security enthusiasts. Welcome back to FatalSec. I am your host, and today we have an incredibly exciting topic to delve into. In this video, we are going to learn how to make use of emulation to decrypt interesting strings present in an Android native library. So let's dive right in. For today's demonstration, we are going to use Momo.apk, which in itself is a testing application that performs various environmental checks on the Android device. If you want to follow along this video, then you can download the APK from our GitHub page, and the link to which I have mentioned in the description box down below. Okay, so here you can see that we have our momo.apk present here. So let's quickly decompile it using apk tool decompile momo.apk. Give it some time to decompile. So here in the Momo folder, we have the decompiled code of this APK, which contains all the assets and the libraries. Let's go to the lib folder inside this. And there we have all the libraries present for different architectures. Since we are dealing with ARM64, so let's go inside ARM64 directory. And here we have only one library present. Before we start analyzing, let's quickly copy this library to our main directory. Copy library, going back to rm library, then momo folder, and there we go. Now if we go back to three directories, we are inside our main directory, and here we have the library. Let's open it up using Radare 2. You can use any other disassembler you like. I usually prefer Radare 2 and Ghidra as my go-to disassemblers because of their open source nature. Alright, R2, then the name of the library, hit enter. Now to start the analysis, we can type A 6 times A basically, and hit enter. Once the analysis is done, we have the disassemble code of the library, which we can see using pd command. Now if we scroll up, we can see all the disassemble code present at this offset, right? Normally all the hard-coded strings were automatically identified by Radare 2, and we can see all the identified strings present in the data and the RO data section of the binary using iz command. Now as we can see here that mostly all the strings are not readable and does not make any sense, right? So it's safe to assume here that these strings are encrypted, and we need to somehow figure out a way to decrypt these strings back to their original form so that we can see what these strings look like in plain text. Best way to start analyzing the strings are by making use of flag namespaces. So let's run fs string command, and then typing F to list down all the strings identified by Radare 2. Right, so here we have all the strings identified by Radare 2 within the string namespace. The idea here is to first analyze the functions which are referring to these strings, and then try to understand how they are being processed in the native library. Based on this, we will then develop our emulation script to automatically print out the decrypted strings without actually running the application on the device. So let's do a quick cross-reference check on any one of these strings. For this one, let's do a quick cross-reference check, and to find the cross-references, we can use axt command and then the offset of where the string is, hit enter. Okay, this string is referenced inside this function twice, at this offset and at this offset, right? So let's see to, let's say, this offset and see what's going on. Enter. So now we are pointing to this offset, right, as you can see here. And let's now display the disassembly of this function using pdb. There we go. All right. Let's try to understand this disassemble code first. So here we can see that this string, which basically is this one, which we are looking for, is being stored in these two registers, x0 and x1. Then it's adding some constant values, most likely to point at some specific index within the string, and then a call is made to this function using bl instruction. If you are familiar from ARM64 calling convention, then you would have already understood by now that these x0 and x1 registers are holding the values which are being passed as an argument to this function, right? So we can assume that this function is going to process our encrypted string. So let's go into this function and see what do we have there. Hit enter. Now again, let's disassemble the block using pdb. All right, let's scroll up and see what's going on here. So it seems like it's quite a big function, taking a lot of arguments and have a lot of local variables. But if we scroll down, can see the last block. So here in the last block of this function, we can see that the string is stored into the X8 register, right? Then it's loading the value present at this memory address into the register D4. Similarly, it's storing the value or the byte present at this memory location into W9 and so on. Then it's performing some OR operations on the values it has loaded in these registers. So we can say that these OR instructions are somehow manipulating the string bytes, and then finally after all these OR operations, the manipulated value is being stored back to the memory using str instruction and strb instruction. Right, but still we haven't figured out what is the final value of the decrypted string which is being stored here, and manually calculating all these values is very difficult and tedious. So we will leverage the power of emulation here. Basically we will try to emulate all this code to figure out what is the final value being written into the memory after decryption, and this will give us our decrypted string. So for emulating the code, we are going to use Qiling Framework, which is a very powerful emulation framework, and if you are not familiar with this, then I would suggest you to go watch my previous videos on Qiling Framework emulation, link to which I have mentioned in the description box down below and also on the top right I button. So that's being said, let's start developing our emulation script in the Python code using Qiling Framework. Alright, so let's name our script as strdecrypted.py. First, we need to import some necessary dependencies. First one is obviously from Qiling Framework. From Qiling, import Qiling. Then we are going to import some Qiling constants. From Qiling.const import ql underscore verbose. Right, and then we are also going to print out the disassembly of the emulated function. So for that we are going to use Capstone engine. It's a very powerful and lightweight multi-platform disassembly framework, and to import that we have from Capstone import everything. All right, now we first need to initialize the Qiling object. For that we have this Qiling method. In the first argument we have to pass the name of our library, which in our case is this one, libmhoshojo.so, right? And then in the second argument we have to pass the path where our ARM64 root file system is present. So in my case it's inside the documents folder, so we need to pass the full path kali documents. Then inside this I have Qiling underscore root fs directory, and here basically I have all the file systems for different architectures. Since we are dealing with ARM64-bit binary, we need to import ARM64 underscore Linux file system. And then finally we can set the verbosity level. Verbose is equal to ql underscore verbose dot off. This constant we have imported from this in the const module, right? Let's store this in ql variable. Okay, so here just to keep the output neat, I have turned off the verbosity level. Now once the initialization is done, Qiling Framework will load the library into the memory, which is of course an emulated environment. So we need to find out the base address where this library is loaded, which we can do using ql.mem.get underscore lib underscore base function. And here we need to pass the path of our library, which we can extract directly from ql object like this. Let's store it into base address variable, and just to see what's the base address we can print it out using print function, library base address base underscore address. Right, let's save this script and try to run it once and see if everything is working as expected or not. So using python 3 and then the name of our script, enter, and there we go. We can see that the library base address is this. This doesn't look like an address, right, because it's in integer form, so we need to convert it into hex. Let's go back to the script, and in our print statement let's wrap it inside hex method. Save, and if we run the script again, this looks much more like an address, right? Nice. Now the next step is to print the disassembly of the function which we want to emulate. Going back to the script. So if you remember from previous videos on emulation, we have to first create a callback function, and then using hook code API, we will tell Qiling Framework to hook all the instruction within the address range we will provide as an argument, and then the register callback will be invoked on every assembly instruction just before it's executed, right? So first of all, let's create this callback function. We can name it as decrypt function callback. This will take three arguments. First one is the killing object, which we will represent as QL. Then the second one is the address of the function. Then finally the size. Okay, now inside this function, we have to use mem_read API to read all the instructions from the memory within this range. ql.mem_read. Here we need to pass two arguments. First one is the address and second one is size. Let's store it inside a data variable. Okay, just to make sure the indentation is right. So now this data variable will be containing our instructions in the form of byte, and to disassemble these bytes into its equivalent ARM64 instruction representation, we are going to initialize the capstone engine. And for that, capstone we have already imported here, and it provides us with a function CS. Here we need to define the architecture and the mode in which we are operating with. Since our library is for ARM64 architecture, so we need to pass CS underscore arc_arm64, and the mode is going to be CS mode ARM. Now let's store it into MD variable, and now we can easily disassemble these bytes using md.disassemble function itself. So for that we have md.disassemble function, and it will take two arguments. First one is the instruction bytes, which we have stored in this data variable, so we will pass that over here, and then the address of the instruction, which we already have in this argument, right? This address will tell the disassembler at which offset these bytes are mapped into the memory, and this function will return an object which contains the disassembled instruction along with other details such as mnemonic and operands. So we need to iterate over this using a for loop for I in, right? Now inside this for loop, we can simply print out all the details. First of all, setting up some format identifiers. Curly braces dot format. Now the first thing we would like to print is the address of the instruction using I.address. Now this would be the address, but since in our disassembler it shows us the offset, so we can convert it into the offset by subtracting out the base address from the actual address like this, right? Then we would like to print out the mnemonic of the instruction, and then finally the operand, which are present inside this op_str variable. That's it. Our disassembler function is ready, and as already mentioned, let's call the hook code API using ql.hook_code, and then passing this callback function as its first argument, decrypt function callback, right? Then in the second argument of this hook code API, it takes the begin address and the end address. And for these addresses, let's create two global variables at the top, begin address and end address. So whenever we want to emulate a function, we can simply just change addresses in these two variables, and the rest of the scripts will work as it is. Now from previous analysis which we did in Radare, we have discovered this function, right, which looks like the one responsible for decrypting some strings. So basically here we are not going to emulate this whole function because it is taking some arguments, and we don't know at this stage what these arguments are going to be, but we already know by now that the last block of this function is the one related to string decryption. So let's just emulate this particular block. So according to this, our begin offset is going to be 28738, right? So let's copy this and paste it in our script here, and the end address is going to be 28770, right? So let's paste it here. Now since these are the offsets and not the actual addresses, we need to convert these into the actual address. So here in the begin argument, we can simply calculate the actual offset by adding the base address to this. So begin address plus base address, which we have already calculated here. Similarly for the end address, we are going to add end address with our base address. Now finally, to run the emulation, we have to tell Qiling Framework with the help of run function ql.run, and that's it. Let's now save the script and try to run it in the terminal and see if everything is working as expected. Python 3 and then the name of the script, hit enter. And what do we have here? Syntax error, empty expression not allowed. Okay, it seems like there is a small mistake we did in the scripts. Let's go back to this print statement, and over here, since we are using the format method, we don't need to specify this f in front of it. Save it again and run it. Alright, it says now begin address is not defined. Okay, small typo. This is going to be begin. Save, run again, and there we go. Looks like we did get something executed. You see error fetch unmapped. Alright, so this issue basically happened because in our run method here we have not specified the range and it tried to emulate the whole binary. So let's fix this quickly. In the run method we will pass the starting address again, which is going to be begin address plus base address, and then the ending address is going to be end address plus base address. Save it and let's try to run it now. Qiling object has no attribute map underscore read. Sorry guys, look, I'm also developing this script right here. It's not prepared in advance. So actually the issue here is because of this mem underscore read. So it's actually not mem underscore read, but it's mem dot read. Clear the terminal, run the script again, and yes, finally. So now it has printed out the disassembly of this particular basic block and we can cross check it. So the first instruction at this offset is ADRP, this offset ADRP, right? This offset add instruction 73C add instruction, right? Then yeah, 2876C, 2876C strp, right? So the return statement is not printed out because the range which we have provided will exclude the last address, and actually we don't want to execute this return instruction also. So this is okay. Great. So now we have a basic working emulation script. Let's modify it to print the string values. But before that, coming back to our disassembled code, let's see how we can identify where our decrypted string is and how we can print it from our emulation script. Okay, so here we have some load instructions and some store instructions, right? Now in any decryption routine, all the encrypted bytes has to be first loaded into the memory using the load instructions, which in this case is going to happen here. Then after doing some processing on it, the decrypted bytes will be stored back either at the same memory location or somewhere else. So in our case, using these str and strp instruction, it's going to store back the bytes into the memory, and it seems that the location is going to be same which has used during the load instruction, right? So we can assume by now that our decrypted string will be stored at this memory address pointed out by X8 register. So one way to print this string is to simply print the value pointed out by the register by hooking at this offset. But the disadvantage of doing this is that we won't be able to scale it for other functions or blocks. But thankfully, Qiling Framework provides us a way to directly intercept the memory read and write operations. Since the decrypted string will be written into the memory, we will only intercept the write operations. And for this, we have an API hook underscore mem underscore write provided by Qiling Framework. So let's go back to our script now, and here let's call this hook underscore mem underscore write API, and this function takes one callback function as an argument. So whenever any memory write operation will be performed, this callback function will be triggered. So first of all, let's create this callback function here and name it as mem underscore write. It takes Qiling object as the first argument, and we need to define the types as well. So it's going to be of type Qiling. Then the second argument is going to be access. Its data type is integer, and it tells the type of memory access, for example whether a read or write operation is being performed. Okay, then we have address, which again is of type integer, and then finally the size. This is also of type integer. And before ending this function, we need to specify the return type, which is none. Now inside this function, let's first make an assert statement, since we are only expecting write operations here. So to avoid our script from getting crashed, assert and then the access type, which we are going to have inside this access variable, and comparing it with uc underscore mem underscore write. And this constant is coming from unicorn constant, so we need to import that from unicorn dot constant import uc underscore mem underscore write. Okay, then to avoid our scripts from getting crashed, let's put a try and accept block. Try accept here, just printing out that an exception has occurred. At this point of time, we don't bother about what the exception is, and inside the try block we will print out our string value. So the value which is being returned to the memory will be accessed via value argument of this memWrite function, which we have missed here. So this memWrite API has another argument which is value. This is also of integer type. Then inside our try block, before printing out the value, we need to convert it into hex form, and for that we can make use of bytes.from hex function. Then we will pass the value and tell it to convert it in hex form using x. Then to convert this hex value into its string equivalent form, we can call decode function. So now this will return as the string, and let's store it in decoded str variable. Now we will print out this decoded string. For that, to print intercepted memory write to, then we will print out the address where the string was stored, right? And then the value is equals to the decoded string, and there we go. So this is our final script, and this should give us a decrypted string. And now all we are left with is to pass this callback inside hook memWrite API like this, and that's it. Save the script, and hopefully this time we are not going to have any crashes. So let's check by running the script using Python 3, then the name of the script, hit enter, and there we go. We can see that these are the disassembled instructions, and then as soon as this stp instruction executed, memory write operation is being performed. Our hook memWrite API triggered straight away, and we can see the value stored by this instruction at this address, and the value is this, right? Similarly, when str instruction was executed, again memory write API triggered, and we have our value. But wait, it looks like these strings are in reverse order, because actually that's how the values are stored in Little Indian format, and by default all our systems use Little Indian format only. So we need to reverse these strings before printing them out. So going back to our script, and in our print statement, right after this decoded underscore string variable, we can put ::-1. They should print the string in reverse order, and there we go. So now we can read our strings. It says unexpected handler unexpectedly return, right? How cool is that? Let's quickly try to decrypt some other string as well. So looking for strings again using F command in Radare terminal. So looking for strings again using F command, and this time we are going to decrypt, let's say this one. Okay, so again we need to copy this offset and look for its cross references using axt command, and we can see that it's being referred at 3 different places. 2 are inside this function and 1 is inside a decrypt function. So the last one looks interesting. Let's go to this offset using seek, and using pdb we can see the disassembly of this block, and we can see that this function looks a lot similar to the one we have analyzed previously, right? So we can quickly go back to our script. Now to decrypt this string, all we have to do is change the begin address and the end address in our script with these offsets, right? So let's copy the begin address and change it in the script, and the ending address is going to be 1D1A4, so we can replace it here. Now saving the script and run it again and see what do we get in the output. And yes, we have the decrypted string from this particular block. So the decrypted string for this value is /data/adb/, right? So this way we can extract the encrypted strings without even running the application, which have a lot of benefits, because most of the application these days are having in-app protections implemented, which prevents the app from being analyzed dynamically. So once we know all the hard-coded strings, we might understand a lot of its working, and we might identify some interesting functions by backtracing these strings. Now coming back to our script once again. So as of now, this script will only print the strings within this address range, right? So every time we have to change these start and end addresses whenever we want to extract the strings from a particular block. And as a next step, we can try to further enhance this script to automatically identify all such blocks which are responsible for decrypting the strings to print all the encrypted strings present in the binary. So I would encourage you to come up with some solutions on how this can be done and let us know in the comment section below. Also, don't forget to subscribe to the channel, hit the like button if you enjoyed watching this video, and we will see you in the next video soon.